everybody. In this DL, we've been talking about relationships between atoms and molecules. We've learned that the way a substance behaves largely depends on the way in which the atoms and molecules in the substances are interacting. The Lennard-Jones potential is a potential energy that describes the way that two neutral atoms or molecules interact. It's not a perfect description, but it makes a pretty good approximation, so we're going to use it in this course. Keep in mind that the Lennard-Jones potential only applies to neutral atoms and molecules, that is, atoms and molecules with no net electric charge. You're going to need to know how to read this graph and how to use it to determine some things, so let's go over the key features. At the end of the last DL summary, I showed you this graph and how we can use it to determine forces between particles at a particular point. But for this video, we're just going to be talking about potential energy. The first thing to note is that this potential energy graph always involves two particles. On the x-axis, we have r. R is just the distance between the two particles, the two atoms or molecules. On the y-axis, we just have the potential energy. As with other potential energies that we've done, the place that we call potential energy 0 is arbitrary. It doesn't matter as far as the physics is concerned. However, in this graph, we've chosen potential energy to be 0 when the particles are very far apart. This makes bookkeeping easy because particles that are very far apart just have no potential energy in between them. There's a couple things to note about this graph that are different from the graphs you're probably used to. Notice what the units in the x and y axis are. Usually we measure distance in meters and potential energy in units of joules or electron volts or some other kind of energy. However, here we have r in units of sigma and potential energy in units of epsilon. So why is this, and what are sigma and epsilon? This graph represents the potential energy between two neutral atoms or molecules. But notice we haven't specified any details about what those atoms or molecules are. It turns out that the potential energy for most neutral atoms or molecules can be modeled in this way. However, the details about how these particles interact depends on the specific type of particle. The shape of the potential energy graph remains the same, but the specific amount of potential energy and the specific amount of distance that the particles have to be apart changes depending on the type of particle that we're talking about. Sigma, in this case, represents the diameter of the particles that we're interested in. A hydrogen atom, for example, has a much smaller diameter than a lead atom on account of the fact that the lead atom just has more protons, neutrons, and electrons. So on the x-axis, the tick mark corresponding to 1 means 1 times the diameter of the atom that we're interested in. Similarly, the y-axis does not have units of energy. Instead, the y-axis is in units of epsilon. Epsilon is called the well depth, with the reason being that -1 times epsilon is always the lowest point in this potential energy graph. Epsilon will change for different pairs of particles. The larger epsilon is, the more negative the potential energy of the two particles is if they're sitting at the bottom of this well, and the harder it would be to pull these particles apart. The bottom of this well is always located in the same place on the graph. It's always found at 1.12 on the x-axis. Remember, because the x-axis is in units of sigma, 1.12 means 1.12 times the diameter of the atom or molecule that we're thinking about. So, for example, if the diameter of the atom was 1 times 10 to the negative 10 meters, then the well would be located at 1.12 times 10 to the negative 10 meters. Broadly speaking, we can break this graph up into two regions, the attractive region and the repulsive region. What this means is that there is a region of the graph where the atoms or molecules would be repelling, and a region of the graph where the atoms or molecules would be attracting. Right in between these two regions, there is a point where there would be no attraction or repulsion between the particles. We've already learned how to use a potential energy graph to determine force. Look at this graph for a moment and see if you can figure out which part is attractive and which part is repulsive. We learned in the last DL how to determine force from potential energy. Force is just equal to the negative slope of a graph of potential energy. So for example, let's look at this region over here. All through this region, the slope of the graph is positive. If you're traveling from left to right, the graph will be going up. This means that the force between the particles in this region is negative. But what does it mean for the force to be negative? It means that the force is pointing towards smaller values of r. R is just the distance between the particles. So a force that wants to make the distance between the particles less is an attractive force. It's pulling the particles together. Now let's look at this region over here. In this region, the slope is always negative. The graph is going down as we travel from left to right. This means that the force between the particles in this region is positive. In other words, it's trying to push the particles apart. Where's the one location where there is no force between the particles? It probably doesn't surprise you that that location is right at the bottom of the well. Right at the bottom of the well, the graph turns around, and so there is a point where its slope is 0. A slope of 0 on a potential energy graph means 0 force. And so if the particles were right at the bottom of the well, they would feel no force whatsoever. Let's imagine what would happen if we had two atoms at the equilibrium distance. We know that when the two atoms are at the equilibrium distance, the force is 0. Now let's imagine what would happen if we started pushing the atoms together. Pushing the atoms together corresponds to decreasing the distance between them. In other words, that corresponds to moving them to the left on this graph. But what happens when we move the atoms to the left on this graph? They start to repel. Eventually, the repulsion between the atoms will be so strong that we can no longer push them closer together. We saw this in an experiment that we did previously. Remember when we had the syringe filled with gas? I was able to compress the gas in the syringe. This means that I was pushing the individual molecules of gas in the syringe closer together. Eventually, the distance between the molecules of gas in the syringe was small enough that the repulsion between the molecules was too great for my strength, and I was no longer able to compress the gas. What would happen if we went the other way? Instead of trying to compress the gas into a smaller space, we attempted to pull the gas out into a larger space. That corresponds to moving to the right on this graph. In other words, increasing the distance between the particles. This graph predicts that if we do this, the molecules will start attracting each other. However, notice what happens if we manage to pull the molecules extremely far apart. While additionally, the attraction between the particles is quite significant, farther apart, the attraction starts to diminish. The slope of this graph never quite reaches 0, but it gets very, very close to it, indicating that the force between the molecules gets very, very small when the molecules are very far apart. This sort of makes sense. If we have two molecules, one on that side of the room and one on that side of the room, we don't really expect there to be any force between them. We're going to be using the Lennard-Jones potential a lot over the next few DLs, so it's worth your time to understand how it works. As always, it's totally fine if some of this didn't make sense to you on your first time through this video. I personally had never understood anything in physics the first time I heard it, so don't hesitate to rewatch this video as many times as you need to help your understanding.